A pleasant good day to you all. Welcome to Discrete Math 101 for this term. My name is Sean Thorpe and I'm your tutor for the next 13 weeks. My email address is thorpe.sean@gmail.com. My telephone contact is 876-446-6050. The textbook you're going to need for this course as a reference point, although I'll be providing you with notes and examples, is Discrete Mathematics for Computer Science by R. Johnson Ball. They have it in 5th and 6th edition, but any of the editions will do. Alright, so let's get started on Discrete Math. I'll give you a quick review of what is to be covered in the 2 modules that we have to do over the next 30 weeks. Alright, so let's get started. Alright, so for this discrete mathematics, there are 2 modules that you have to do, and each module is weighted on 100% of coursework. You have no final exams, you have no tests, you only have assignments to do. Specifically, in Module 1, the topics to be covered at 100% of coursework, which you will be getting in the current week, will be covering the areas of complexity analysis, mathematical induction, equivalence relations, and inclusion-exclusion principles. So hence, really over the next 4 weeks, we'll be covering this body of work, and the assignment, I must assure you, takes about a month to complete. So they are issued at the start of the classes or at the start of each module. And because it takes 4 weeks to complete, I do recognize that the importance of time is very relevant. Of course, this is my favorite course, Discrete Mathematics. I love it dearly, like sliced bread, and I hope you will too. Okay, so let's get started. Alright, so before we jump into the content of Module 1, some of you may be asking right now, why is this course in Discrete Mathematics for Computing really necessary? Well, some of the big topic areas that you hear today, like machine learning, artificial intelligence, cybersecurity intelligence, computer networking, are all built on the foundations of discrete mathematics. When I'm finished, you're probably going to say, why wasn't this course introduced first in my curriculum? Literally, it's a course you're doing in your final and 4th year here at DTDI. And the argument is that you will see as we develop the different topic areas why these are some of the areas to which the mathematics itself is highly relevant. So again, areas like machine learning, artificial intelligence and neural networking, cloud big data to provide cybersecurity intelligence, and large-scale computer networking. Those 2 modules that we'll be covering in this course have high levels of relevance to these things, right? Computer system performance and modeling based on the networks that you have configured all relate to areas of discrete mathematics. So I'm saying again, for the record, discrete mathematics is the nicest thing since sliced bread, and our objective is to treat it as such as we go through the content over the next couple of classes. So for Module 2, we'll be looking at graph theory, and the subtopics relating to graph theory will be properties of graphs, for which we have 8 of them to look at. There's the applications of graph, and there are use cases of graphs that we'll be verifying. This is a very big topic, especially when you think about simulations in computer networking. It's a very big topic. It's also 100% by coursework, so I will need you to spend the courtesy of time engaging as we will have engaged Module 1. The assignment will also take 4 weeks of engagement. So let's get started now into Module 1. Let's start with complexity analysis. The mathematics of complexity analysis is that everything on the planet can be evaluated as a function of time in some shape or form, and that measures the performance. That measures the performance of your environment. So in computing, we measure the performance of everything. When you did programming, we would compile and execute at runtime. That performance is really a mathematical function which we'll describe as f of n. And for those of you who did pre-calculus and calculus, you remember this limit symbol of approximation. F of n will be approximately of order g of n. So therefore, all the smaller performance tasks, which is related to f of n, will be its g of n function. And O is the order of complexity of the function. We'll now spend some time breaking this down into more careful detail so we can appreciate where we are going. As it relates to complexity analysis, we now have to look at a performance scale. And that performance scale, very specifically, ranges from log of n, which is the log of a number. That describes our best case, ideally. So the log of a number, as you may remember from pre-calculus and calculus, is that log of a number gives you a smaller number, which to the machine improves the overall performance and runtime. Sooner or later, I'll describe log n as Usain Bolt, to use sports as my analogy. And then the performance gets worse. Probably as it gets worse, the average case could be what? Yolande Blake in the middle here. And if it gets worse, I could argue, and some of you may dispute me, that this could be a Salford power at the end, which is n factorial. So anything n factorial is the worst case because it will take the longest time to finish the race. So if a Salford comes in last in the race, he's at what? N factorial. And everything coming back this way towards log n is the best case because that is going to be Usain Bolt. If we treat the mathematics like that, you will have a great time this semester because all these computation of numbers in the form of logs, n log n, n squared, n cubed, 2 raised to the power n, and n factorial as a function of mathematical real numbers are nothing more than assisting us to understand the performance scale of various efficiencies. So let's get going with this very exciting topic. So in the context of the complexity scale, a function which is log n or n log n or n squared all the way to n factorial from before, we can treat it in the context that that is a function of f of n, which is approximately of order g of n. So f of n will represent what we call our total cost path function. This is the approximation symbol which you are familiar with from pre-calculus and calculus. And then O, as indicated here, is the order of mathematical complexity. So we'll be going through each of these. Then my next turn is for us to look at the g of n, which we'll do that in a minute. So a function which is f of n approximately of order g of n, the g of n component is really nothing more than a subset of f of n. So let's use an example as I have on the board. So therefore, my total cost path operation will have some operation in n squared plus some operation in n plus some operation as what? 1 over n. A very simple example to use is that we are going to run a 100-meter race. And the length of time that is going to take to run that 100-meter race will be dependent on these 3 candidates running the race. One guy called n squared, one guy called n, one guy called what? 1 over n. And all of that represents my g of n operation. That will be mapped back to the f of n. So who can guess who is Asafa, who is Johan, and who is Usain? We will see that in a moment, because the expectation that we are going to now develop is to determine the length of time that this f of n function will take to execute, right? This, of course, could be a server running n squared, another one running at n, and this could be another server running at 1 over n. Our main objective is to figure out which one is taking the shortest time, which will be the best case, which one is taking the longest time, which will be the worst case. So we will see, and as you have actually observed from the big O complexity scale before, we can map the behavior. We are now going to spend some time looking at how long it's going to take to execute this f of n function as a problem. So when I look back at my big O complexity scale, log of n being the best case and n factorial being the worst case, it should be very important to note that f of n is approximately then of order n squared plus 1, n plus 1 of n, 1 over n. As a reminder, people should note that 1 over n is the same thing as what? The log of n. Alright, that's from pre-calculus and calculus. Just a kind note. 1 over any number, right, will give me a smaller number, especially if n is a large number. We'll see that in a moment too. So here we have it, that if f of n is approximately n squared plus n plus 1 over n, the purpose of the complexity analysis is to determine which one of these three guys will take the longest time to execute, or which one is moving closer to the worst case, which is in my other direction. Here we will see that n squared is much what? Larger than what? N, if we look at the scale, n is here, n squared is here, which therefore means that n squared is going to come in at a worse performance than what? Than n. And similarly then, n squared rate is much greater than n and much greater than what? 1 over n, therefore means that the functional complexity of this operation is such that f of n is approximately of order n squared, because n squared is going to come in last. Another way I could say this is that this guy is a Safa, this guy here in the middle is Johan, and 1 over n is who? Usain. Usain basically runs at a faster time compared to what? N versus n squared. When Usain finished running the race and Johan finished running the race, who is still left to come across the finish line? N squared. So therefore, the length of time that the entire race would take to finish running would essentially be the fact that n squared's operation is the largest one, and hence f of n is approximately of order n squared, to suggest then that who? Asafa came in last. And because he came in last, it meant that that took the longest time, or that is the worst case performance for executing this race. So I use those three candidates to represent a race, and of course we know that races are computed based on times, and therefore that's a computer operation. So these could be servers, these could be switches, these could be network operations. What we are saying, oh, that's why I said math is the nicest thing since sliced bread. We can use the basic operation of the math to demonstrate the outcome of what your total operation will take. Alright, so just to reiterate, a function which is of f of n is approximately of order n squared plus n plus 1 of n. The objective is to find the operation that takes the longest time based on this big O complexity scale. Let me repeat that. The objective is to find the operation that takes the longest time. Mathematically, n squared is a larger operation or a longer operation than n. N is a longer operation than 1 over n, which I said before is the same as the log of n. Alright? And of course, this double greater than sign is to suggest that n squared is much greater than. Alright? Not just greater than. Much greater than n, and n is much greater than 1 over n. Hence, f of n is approximately of order n squared is definitely suggesting that n squared took the longest time of the three elements to execute. So let's look at some more concrete examples as a part of doing the first problem in your assignment set for Module 1. Alright, so here's our first problem example set that we want us to work through. So the exercise says, show the big O complexity of the following. It's also called big O complexity, or the big O order of complexity. of the following. For all values of n belonging to the set of positive real numbers. Yes, this upside down V with the cross here, you have done this as well from pre-calculus and calculus. So for all values of n, where this is the member of sign, and this sign here will be looking like an R with the plus beside it, indicating that these are the set of all positive real numbers. I remember what a real number is, right? It's a whole number, right? And the possibility that you can have fractions. So it can be a whole as well as a fraction within it. It represents a set of real numbers. And in real life, all numbers in terms of a computing operation is a positive real number, not to be mixed up with natural numbers and otherwise. So the three problems that we're going to look at here is f of n being assigned 2n cubed plus n squared plus n versus f of n being assigned n cubed plus n squared plus log of n, which by hint is the same as 1 over n, and f of n here being assigned what? N squared plus 2 all into n plus 4. So let's get started. So for f of n equal 2n cubed plus n squared plus n for all values of n belonging to the set of all positive real numbers, and do remember that positive real numbers are like from 1 to positive infinity. In this case, based on the big O complexity scale, look back in the earlier part of the lecture, n cubed would be much, much greater than n squared, which would be much, much greater than n. Therefore, what we're seeing based on the problem, it also means then that what? 2n cubed would be much, much greater than what? N squared, much, much greater than n. So we need to find the condition for that. So step 2 is to test for a real number. We didn't start off with any early test number, but we're now in some live examples. So we start for when n equal what? 1. We could start there. And some of you might argue why we start there, because 1 is a positive real number. 2 plugged in for wherever I see the value of n, this is going to be 2 times 1 cubed, which is still 2. So 2 is greater than 1, but 1 is not greater than 1. So hence it is not true. So what we'll have to now do is do another conditional test for when n equal 2. See again, when n equal 1, 2 is in fact much greater than 1, but 1 is not greater than 1. And hence that's why we are not saying that this is yet final, because all points must be tested to show true in order for us to know that it is true. So we'll now test for n equal 2. So when n is equal to 2, what we simply do now is wherever we see n, we put the value 2. So this becomes 2 cubed. So 2 times 2 cubed is much, much greater than 2 squared, which is much, much greater than 2. Of course, 2 cubed is 8, 8 times 2 is 16. 16 is much greater than 4, is much greater than 2. Hence, this is true. Alright? And hence, we can now make the final deduction that supports the truth of this f of n function once and for all. So let's do that. So in step 3, which is our final solution, we see that from step 2, only when the values of what? N is greater than or equal to 2, we have a solution in f of n, which is approximately of order what? 2n cubed, right? Because remember, we're looking for the operation that took the longest time. So therefore, it's approximately of order 2n cubed for all values of n belonging to the set of what? All positive real numbers. And notice the test conditionality is when the value of n was what? Greater than or equal to 2. So the operation was only effective to tell us what is the worst performing operation based on the value of n greater than or equal to 2 and not before. So this represents the solution to the first example. Let's do the second one. Okay, so class, let us look at the second problem now that we have done the first one. F of n is equivalent to n cubed plus n squared plus the log of n, where we are saying, using the upside down looking v, for all values of n belonging to the set of all positive real numbers. So the solution step that we're going to carry out right here is that when we start, we say with step 1, we contend that we have n cubed is much, much greater than n squared, which is much, much greater than the log of n. When we take that down one more step, that becomes n cubed is much, much greater than n squared, which is much greater than 1 over n. As a reminder from pre-calculus and calculus, that what? log of n is the same as 1 over n. Alright, now when we move to step 2, what obtains is that we must now test for one of those positive real values of n. And we can start at 1. I'm deliberately going to start at 1 to show you a conditionality that you may also come up with in your problem solving. When n is equivalent to 1, we can substitute back into the equation that n cubed, which is the same as 1 cubed. 1 cubed is much greater than 1 squared, which is much greater than 1 over 1. That is definitely false. So we are seeing so far, for this particular problem, this does not hold true. So we are now going to have to test for a value of n greater than 1, and we now move to a value for n equal 2. So let's do that in a moment. So as we can see in step 2, we must now continue as it relates to finding a value in n that is suitable to determine when this particular condition is true. Remember, this is a big O scale, and we know from the big O scale that n cubed is likely to take the longest time. So our solution is to demonstrate or show the truth of this particular scenario. So when we say n is equivalent to 2, seeing that when n was 1, the entire condition was false, we are now seeing that when we plug n at 2, we get 2 cubed, which is much greater than 2 squared, which is much greater than 1 over 2, because we are simply substituting for the value of n. That works out to be 8 is much greater than 4, is much greater than a half. This conditionality is true. Hence, now when we move to our final solution step, we can say the longest time that f of n function is going to execute is approximately of order of complexity n cubed, because that's the biggest operation. We are suggesting then that for when f of n is approximately order of n cubed, for all values of n belonging to the set of positive real numbers, we are seeing that this is only going to hold true for when values of n is greater than or equal to 2. When you're doing your problem solving, you have to take this similar approach because we have to test for those conditionalities. Alright? So let's take up another problem and continue the exercise to ensure that we get these steps quite clearly. So we're going to look at problem 3 now. So let's look at the third problem. The third problem is n squared plus 2 into n plus 4. And this again is for all values of n belonging to the set of positive real numbers. We are suggesting as step 1 that we expand the brackets, because as you can see we have a factoring. When you expand the brackets, we get n cubed plus 4n squared plus 2n plus 8. And that should be obvious for all of us. We simply expand. N squared times n give us n cubed. N squared times 4 give us 4n squared. 2 times n give us what? 2n. And 2 times 4 give us 8. Accordingly, what this now means is that this particular function in f of n is now n cubed plus 4n squared plus 2n plus 8. Using the same principle of the big O scale, n cubed is much greater than 4n squared is much greater than 2 of n. And of course it's going to be much greater than 8 because 8 is a constant. We don't really need to put the constant, we're only looking for the terms in the complexity scale in n. Alright? So let's continue this in a moment. In moving to step 2, we can actually now test for the values of n. Remember, n belongs to the set of all positive real numbers. So I can start with 1. And you might say, sir, why are you always starting with 1? I don't. The idea is starting with 1 just to show some basic proof cases, but we'll see as you do the actual assignment problems, you could actually skip the value of n from 1 to 2 or to 3 as a bigger number. But I'm deliberately going to use 1 and 2 probably for this one based on its complexity. So when I test for n equal 1, we have 1 cubed is much greater than what? 4 times 1 squared much greater than what? 2. That still works out to 1 being greater than 4, being greater than 2. No, sir. That is actually false. So because this is false, this condition will not hold true for the problem. So we go now and we test for what? N equal 2. We plug in the value for n equal 2. We get 2 cubed is much greater than 4 times 2 squared is much greater than what? 2 times 2. That's the same thing as saying 8 is much greater than 16 is much greater than 4. No, that is still false. Well, by looking at it, we are going to have to test now for n equal 3. And let us see if when we test for n equal 3, it holds to be true. Now, because n equal 1 nor n equal 2 work, let's test for n equal 3 as a continuation of step 2. So when n equal 3, this becomes what? When we substitute, 3 cubed is much greater than 4 times 3 squared is much greater than 2 times 3. That works out to be 27 is much greater than 36 is much greater than 6. No, still false. Alright, we test again for when n equal 4. That gives us 4 cubed is much greater than 4 times 4 squared, which is much greater than 2 times 4. That works out to be 64 is much greater than 64 is much greater than 8. Still false. 64 is not greater than 64. So we move now down to when n equal 5. This gives us what? 5 cubed, much greater than what? 4 times 5 squared, much greater than what? 2 times 5. Finally, we now see that 125 is much greater than 100, is much greater than 10, and hence true. So this is what we will now use to fashion our final solution step. Just in a moment. So, in step 3, which is the final step, f of n is approximately order of n cubed for all values of n belonging to the set of what? All positive real numbers. And that's only true for when the value of n was greater than 4, or in this case where n is greater than or equal to 5. So therefore this now constitutes my final solution. And all the steps we did before were very important to get to this point. And hence in the assignment problems that you will have, I would like you to follow this religiously as a part of your own approach and effort. Anyway, I have put 2 more problems here for us to consider. I will do one of the 2 as a starting point. Look at this one, a different order of operation. F of n is equivalent to n squared plus n all into n plus 3 over n to the 5th. And the next one is f of n is equivalent to n cubed plus n squared into what? N plus 2 all over n squared. I want you to determine the complexity of these 2 functions. Where is f of n tending towards? I'll start with the first additional problem though, just to ensure that everybody remembers how to separate and handle these fractions, alright, as a courtesy. So let's start with the first additional problem. And I sincerely hope you follow all the steps we were doing before, and you go through these pre-recorded lectures in such a way that you spend the time appreciating the step-by-step approach that we have been taking. So we're taking a slightly different problem where we have a fraction. So here we are saying f of n is equivalent to n squared plus n into n plus 3 over n to the 5th. Alright, step 1, we will need to expand the brackets as it relates to the fraction. So we take the numerator piece, n squared plus n into n plus 3. N squared times n give us n cubed, n squared times 3 give us 3n squared, n times n gives us n squared, n times 3 gives us 3n. Of course, when we take that down, this becomes n cubed plus 4n squared plus 3n. Remember, 3n squared plus n squared gives us what? 4n squared. So n cubed plus 4n squared plus 3n. Please do not forget, the entire thing is separated by a denominator here, which is n to the 5th, so I put it back. Now, looking at this, I would argue that we can still simplify this even further. So we'll continue that in a moment. Alright, so in moving to step 2, what we can now do is simplify n cubed plus 4n squared plus 3n all over n to the 5th. Now because n to the 5th is a common denominator, it's simple to say that we have n cubed over n to the 5th plus 4n squared over n to the 5th plus 3n over n to the 5th. See that? Because n to the 5th is common to each of them. Such that when I reduce this, and for the power of indices apply here, pre-calculus and calculus, for those who don't remember, n cubed over n to the 5th is the same thing as what? 1 over n squared, because I'm subtracting the indices. Then I have 4n squared over n to the 5th is the same thing as what? 4 over n squared. 3n over n to the 5th is the same thing as what? N raised to the power 4. So now, this is what we have as the reduced equation. So we move to step 3 to further simplify. As a reminder, based on the big O complexity scale, 1 over n is equivalent to the log of n. Some pre-calculus there, some calculus there. So 1 over n squared is equivalent to the same thing as what? 1 over n multiplied by 1 over n. Which therefore means that 1 over n squared is also tending to what? The log of n. Similarly, 4 over n squared is also tending to log of n. Only thing, it has a coefficient or a constant value of 4 as in the numerator. So this is now what? 4 log n. Let's continue this in a moment to actually deduce the final piece, which is 3 over n to the 4. Alright, so in continuing step 3, the last term we had was 3 over n raised to the power of 4, which is the same thing as 3 over n squared times what? 1 over n squared. Some of you must be saying this looks rather discrete, which is why we call it discrete mathematics. 3 over n squared times 1 over n squared. This is indicative that the 1 over n squared term is a log n term. So 3 over n squared is a log n term. 1 over n squared is a log n term, which works out 3 to the log n. What we see then is that all the terms have reduced to log n, such that when we go to step 4, and unlike the previous problems, once all the terms reduce to a single term, there's nothing more to show. So therefore, since all the terms in step 3 are simplified to log n, the complexity, the big O complexity of the function f of n is such that f of n is now approximately of order log of n for all values of n, which actually is a member of the set of all positive real numbers. This now represents our final solution. This now represents the outcome to the first problem in the additional problem set that I've given you. So I'm going to encourage you on your own time now to take the second problem, work it out, and you can send me that solution as an encouragement to demonstrate that you really appreciate what we have been doing here. Alright? So we're going to move on to the next subtopic shortly, which is the whole area of complexity loops. How in computing we apply these even further as a part of problem solving. Alright, so we're going to start the whole topic of complexity loops. We can evaluate the behavior of loops just as how we looked at the big O scale and show the performance of functions. So a computer program, mimics the similar behavior. So we can have a linear loop function which executes at an order of n. Alright, that's linear. Here's an example. We have a for loop. This is a little bit of C++ code snippet. This is not a compiled program. Let me remind everyone, for those who are great compilers, you can actually go and take this and compile it otherwise. So for I starting at 1 and I less than or equal to n, the loop here is going to execute n times. So therefore, the order of complexity in this case goes to what? Order of n, because it's going to execute n times and then print out the asterisk, as you can see here. The asterisk is just basically semantics for the purposes of demonstrating the behavior of the loop. So we can have a loop that executes order of n. Of course, this is an average case complexity in a traditional computer program, but at least we get the idea of exactly how our program should be performing. Now let's look at the others quickly. The second loop that we want to look at is the quadratic loop. So we are continuing these complexity loops. This particular loop executes at order of n squared. So clearly it's a worse performing loop. So the example, I have a for loop. The first for loop, I starting at 1 executes to n. That's the linear property. And then the second for loop, j starting at 1, j less than or equal to n. That's also executing order of n because each loop goes up to n times. What we are going to do is multiply the outer loop by the inner loop just to print that asterisk statement, which means when I take the outer loop, which is order of n, multiplied by the inner loop, which is order of n, this is now going to give me a final result here of f of n being approximately what? Order of n squared. Now that's quadratic, isn't it? That's quadratic. So let's move to the polynomial loop next. Third loop category is the polynomial loop. This one executes at an order of n cubed. It also could be higher, but let's just demonstrate the basic examples, like some that I have in your assignment problem that you need to deduce for me. right? So for I starting at 1 and I less than or equal to n, executes what? I number of times. That first loop is order of n. Then I have an inner loop here, which was executing to j, order of n time. And then I have a third loop now, executing k all the way to n, order of n times. What we simply do is multiply the outer loop by the inner loop, so we'll get f of n being approximately order of n times order of n times order of n, which is going to give me order of n cubed. Alright, let's move on. The next loop we would like to look at is the logarithmic loop. This one executes at an order of log n. Of course, this is a best case outcome of a loop. Here's the example. So for I starting at 1, executing to n, each time I now increments by what? A multiple of 2, or it could be some other multiple. What it then means that the function f of n will be what? N over 2, because each time around it's going to execute twice as fast. So when it executes twice as fast, notice n over 2, n over 4, n over 8, this function in n becomes progressively smaller. So therefore the entire size of f of n moves towards approximately log of n. So for those who are programmers who would normally write loops, once you increment the value of the loops by a higher value than 1, traditionally what you will see is that the loop execution time becomes what? Smaller. When the loop execution time becomes smaller, it moves in factors of n over 2, n over 4, n over 8, which, as you would have known from the previous classes, these tend to move towards a value of what? Log of n. So we'll now look at linear logarithmic loop as the next example to this one. So let's do that in a moment. Linear logarithmic loops is the next one. This one executes at an order of n log n, which is now much closer to the best case complexity if we think about the big O complexity scale. Here's the example of the loop. And hence, as a programmer, this is how you should be writing your programs, with these kind of mathematical complexity considerations in mind. So for I starting at 1 and I less than or equal to n, I is incremented by 1. That's the ON function there, or the order of complexity n there. That's a linear portion. And then the second loop, you notice it is behaving at an order of complexity. Okay, I made a update here. This should be plus equal 2, right? So it shows that the operation is in multiples of 2. Therefore, this is for I starting at 1, I less than equal to n, I plus equal to. That's the log n operation. So when I multiply the outer loop by the inner loop, which is the order of n by the log of n, I'll get back what? N log n, which is demonstrating the linear logarithmic complexity. So we'll now move on to an example of probably a linear quadratic loop or that type of thing, right? But I probably might just leave it there and give you some examples to do on second thought, some additional examples as problem sets, all right? So we have really come to the end of complexity analysis as a lecture. Just to summarize, this whole topic of complexity analysis in computing has to do with what we call performance computing. We use the complexity analysis based on function, based on scale, to evaluate the performance of various operations. What we did, we looked at some applied problems. I'm encouraging you to spend some time looking back through those problems that we've been doing, the solutions that we actually unearthed working on those problems, so you can actually reinforce the concepts that we have been discussing in this first lecture, right? Then we looked at complexity loops, which is really programmatic loops. You know, you write a program, a traditional computing program in C++ or Java, or whichever the language that you have to write. The behavior of those programs and how well they execute at runtime on the physical machine is as a result of the mathematical complexity of these function operations. You may not have known that before, but the idea is that as you move into the field of work, the intention should be very clear that we can apply complexity analysis in meaningful ways to solve very interesting problems. Of course, in the assignment that you get for Module 1, you'll have one entire question that focuses directly on the whole area of complexity analysis. And I would get started on them if I were you. because by the start of the course here, you would have also received this corresponding assignment. All right. So we'll now be moving our attention from the whole area of complexity analysis to another form of analysis, which is called mathematical induction. And mathematical induction, in our second lecture, we will be looking at some basic proofs in terms of how we can use those to determine simple predictions. Simply enough to what in artificial intelligence that is used today, but that is actually our follow-up topic shortly at the end of this one. So I hope you found the topic one here interesting. I hope you are finding discrete mathematics an interesting subject here. I usually say some nicest things in slice bread. I hope you will be saying the same thing as of now and going forward. So I look forward to seeing you to the start of lecture 2, and we'll be going straight into mathematical induction accordingly. Remember, start going back over those applied problems that we did in this lecture. Pay attention to the care and the discrete nature of how we resolve those problems. All right, thank you. Let's move to lecture 2.